We have one chapter left to do. We have now finished chapter 15. It was non-parametric. And we need to do chapter 17, which is the control statistics. Like I said, I finished chapter 15 last time. And you have a homework assignment in, what's it called? Launchpad. I always want to call it Stats Portal, which was the last version. But that one does not have Kruskal-Wallis in it, and I told you I would have an assignment for you next week over the Kruskal-Wallis test. And so I haven't done that yet. And I leave tomorrow morning and won't be able to do anything until early next week. So if I get it done for you tonight, then it's going to have to be next week before I get a Kruskal-Wallis problem out there for you. But do you have a question?
On the homework, where it asks for the p-value, that part might be messed up because
it wasn't accepting the p-value that you put in?
It doesn't ask for a p-value. It won't ask for a p-value, but it gives you the option of less than 0.05, 0.05, or 0.1, or more than.
Ah.
And
so it doesn't ask for an exact p-value. It just says decide if it's above the cutoff or below it, and then.
So the first time I used less than 0.05 and got it wrong. The second time I went greater than 0.1 and got it wrong. And then so I don't know if I'm doing something wrong. But also that says that the sample size is 10, but there are only 9 differences.
So the sample size is off by 1? Anybody else notice that?
I did.
I didn't notice that.
But I noticed it.
Yeah, so yeah, boy, I get so many emails about this that I can't keep track of them all, but just do the best you can on it, and then if you get marked wrong,
I mean, I still have another try. So
another attempt. Yeah. So screenshot what you did, or what you if less than 0.05. You tried greater than 0.1, that only leaves in the middle, so it may be the sample size problem made their p-value slightly bigger than what your when you did it in SAS, was your p-value less than 0.05? Yeah.
No, I didn't do it in SAS.
Oh. Yeah, that's right. Yeah, it could be a continuity correction kind of thing, but yeah, I wasn't aware that there was one that was so borderline that it would cause it to go above or below 0.05. So,
this might be a dumb question, but how would I do that?
We don't have data.
Yeah, I can't remember the question off the top of my head exactly what I had in there, but and I'm not logged on. It would take me a little while to get logged on to pull it up, but.
I mean, we don't have to do it right now.
Yeah. Okay. Well, just keep track and take screenshots if weird things happen, and email me with questions, and I'll try to get you answered before the deadline. When is the deadline? Tonight?
Tonight.
Yeah. Okay. So.
Unless you want to make it next week sometime. Which...
No, I don't want to do that. All right. Any other questions?
Oh, grades? Do you have somewhat recent grades?
Yeah, I just a couple of days ago went through, downloaded the grades out of Launchpad, so I have those, and then so all those technology assignments I did, you should already know what your grades are on those because I've emailed those to you. I haven't got that second project graded yet, but other than that, I think I'm all caught up. But I've downloaded the grades out of Launchpad, so in my grade book, I now have all of it put together, so I can tell you what your homework grade is. But for the most part, your final grade will be 80% tests and 20% everything else. And so you can kind of, since we've had 2 tests at this point, your average of those 2 is pretty close to what your grade is. So, all right. So, before I start chapter 17, I want to start with the group project number 3. Since Friday, that's what I'm expecting you to do while I'm gone. We'll get that going today, and then when we finish with that, we'll start chapter 17. Okay? Now, here's how it's going to work. I've got 3 different project direction sheets made up, and I'll give one to each of 3 groups, right? Because we've been using 3 groups. And I have a different data set for each of those 3 groups, and then I want you to run an analysis of that data set and write up the results, right? So the write-up will be at least as important as everything else, right? So use good English, good grammar, and let me go ahead and open one of the documents. They all 3 will look similar. So here's Group 1 project document. And they all 3 deal with baseball data. Right?
Peyton has affected you.
Yeah. I actually started using the baseball data before Peyton was ever in a class, but there was another baseball player who was actuarial science before him, and he kind of got me going on some of this stuff. But what I have 2 data sets that I actually built myself off of, what's it called, baseballalmanac.com. Have you been there? You've seen that website? And it has just everything you could ever want, way more than I could get. But I created a data set from the 2012 season. The first time I used it was, I think, 2013, so it was the next year. And it took me a long time to build it, so I don't do it every year. But
We have that one?
no. We're going to randomize. But what's in this data, two of the 3 projects deal with this data set from that year. The other one deals with data that comes from 1992. And that's data I've had for years that I didn't build. I got it from another stat teacher on the web. Hey, here's an interesting thing for your statistics classes. So I had that. But all 3 groups will do a similar thing. It's just the data is a little bit different. So this one is for non-pitchers. So the idea is, those of us that know anything about baseball know that there's certain statistics they always keep. What's their batting average? How many RBIs do they get? Those kind of things. Fielding percentage. And so the question is, some players get paid a lot more than other players. And why are they getting paid more? Is it because their batting average is higher? Or is it because, so we've got a big data set with lots of information in it. And so you're to analyze that data and figure out which variables are the best predictors of what the salary is, right? So the data is from 2011, and then you're trying to predict what their salary is the following year. Now, right away, there's a problem with that if you know anything about how professional sports works, right? What's the problem? Well, the Royals just went through it. They had to re-sign, say, Alex Gordon, right? And they signed him to 5 years. So what he does this year isn't going to affect his salary next year, right? So one of the most important predictors that's not even in this data set, so you can't use it, is, are they up for free agency? If they're up for free agency next year, then that's a big predictor of what their salary is, right? So just while the contract is under negotiation. But anyway, you you don't have to think of it as their salary is a response variable so much as just, is it correlated, right? Is the salary that they're receiving correlated to how well they're doing on the field, right? And then which statistics seem to go along with the players that tend to get paid the most. So if I scroll here a little bit, for non-pitchers, the statistics that we have are how many games they played in, what is their batting average, what's their slugging percentage, all those things. If you don't know what, I have really cryptic descriptions of these things, like OBP is on-base percentage. If you don't know what those things are, it's probably not going to kill you that much in terms of doing this project, but it's worth a little Google search to see how some of these things are done if you're interested. But feel free to ask me about them also. So those are batting statistics, all of these things, strikeouts, base on balls, the usual things, and then fielding statistics, put-outs, assists, errors, whole range of those. Not as many fielding things as there are batting things out there, but okay. So then it says your group is to retrieve the data, determine whether there's a relationship between salaries and performance. All right. So you'll have to decide on what kind of statistical methodology you would use to answer that question, then run it and make your conclusions. Right? So the report should contain conclusions and rationale with regard to an ordering of performance variables. This one's best, this one's second best, kind of thing. See what I'm saying? Okay. I did put a little hint in here. Salary data is highly skewed. What does that mean?
There's outliers.
Okay, there's outliers. So what does a skewed distribution look like? Like there's a big hump and then a really long tail, right? So professional sports, not just baseball, but most professional sports sort of impose a skewness too, because there's a natural wall. There's a minimum salary. And I don't remember what it is for baseball, but I think it's like $200,000 a year. So nobody gets paid less than that, right? And most of the MLB players clump up fairly close to that minimum. You hear about the $1 million, $2 million, $12 million salaries. Those are the outliers, right? So you get this real skew. So I'm making a suggestion to do a log transformation, right? We talked about transformations of data earlier in the semester. We didn't do a whole lot with it. This is data where you should do that. All right, so salary data often, even if it's not sports, it's, CEO salaries or whatever, it's always going to be skewed because you can go high, but you can't go below zero. So it's going to be skewed. Do a log transformation. So I can't remember if I have a variable in there already, log salary, but if not, you'll have to create one. So you can create it yourself within SAS. The data right now is already converted to SAS, but you can export out of SAS into Excel if you want to manipulate it, then read it back in to SAS. If you don't like, or you can't figure out how to add variables in SAS, then you can do it that way. I probably also have the Excel versions of these if you want that. But all right, so then the requirements. The report requirements describe the process that you used, right? So, yeah, I don't have in here a basic outline of a paper, but most, what's the word? Scientific research type papers that you'll have to do, right? And even when you're on the job somewhere, if you have to write up the results of an analysis, you're going to have sort of an intro section. You're going to have a methods section. So intro is just explaining, here's the problem, right? I got major league data, blah, 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 I want to do this. Then the methods section is, here's what I did, right? Or here's here's the approach we used. It also describes how the data was collected, anything like that. Well, this data was already collected for you, so you won't have too much to say there. But, and then after your methods section, you should have a results section. And the results section gets pretty detailed. That's where the bulk of the paper is going to be. It'll tell, I fit this model, and here were the results. I didn't like this variable, so then I fit this other model. All the steps that you went through. It should have graphs and figures. I guess that's the same thing. It should have graphs, and it should have possibly some tables that maybe, like if you do a multiple regression model, you might have a table that shows the name of the variable, its parameter estimate, its p-value, right? And then your conclusion about whether that's a significant predictor or not, right? So tables like that. But then after the results section, usually in a results section, you don't say a whole lot about the implications of what you're seeing. You don't editorialize. You just say, here's what I got. Then you have a discussion section as the final section, right? Or sometimes it's called conclusions. Sometimes it's called discussion. Sometimes there's one of each. A lot of the medical stuff that I do has a conclusions and then discussion. You don't need both of those, right? So the difference is, conclusion is, what can I say about the results of my statistical analysis, right? I can say there is sufficient evidence to conclude, those kind of statements. And then discussion is editorializing what you think that means in the population. You can kind of combine those. Right? So everybody understand what I want for results compared to discussion? So discussion should be fairly short, a few paragraphs, and just say, in the end, here's what I've concluded. Okay? Hand in one final typed paper per group. Now, it can be on paper or it can be electronic, but it needs to be like a Word document or a PDF file or something that's electronic. That's not handwritten. That's what I mean. It's not handwritten out on paper. This is like you would do this for your boss, right? If you've been asked to analyze a set of data, and okay, here's what we found. You've got to turn in a report. Okay? Now the fun part. After the paper's written, you will do a 10-minute oral presentation. Right? So I got 3 groups, and we'll probably do this over one 50-minute period. So 50 divided by 3 is about 15 minutes. Right? What's that? 17.5. Yeah. So about 15 minutes. This says 10 minutes because there's a little transition time in between getting one group done and the other group up and get their presentation loaded and all that. If it has to go over into a second day, that's not a problem. So I'm not gonna hold you strict. People always go, gosh, I'd rather do 10 minutes than 15 minutes. But in truth, when you actually give public presentations, what you find is you wish you had more time, not less time. It's awful easy to run long. It's rare that you don't run the full time. You know what I mean?
Pacing is an art.
What's that?
Pacing is an art.
Yeah, pacing is an art. That is true. It's hard to do. So I'm not going to hold you too strict on that. Right?
I will, though.
Yeah. Got a watch and a gong. Right? And so these will be due on May the 2nd. That's the first day of what we call dead week. Right? That's the last week of classes before finals. So no papers are supposed to be due during that week or assigned during that week. So I want it handed in as that week starts. Then you'll do your presentation probably that day. If it goes to Wednesday, that's fine. And then whatever else of the week we have left, we'll use to review for the final. Right? So we'll take whatever we need to do 3 presentations most of the week will be spent on reviewing for the final. All right? So I said in here, PowerPoint slides. You need to have PowerPoint slides. It doesn't have to be PowerPoint, but some kind of presentation slides that you can show up here on the screen and go through. Everybody in the group has to participate, not only in writing the paper, but in presenting the paper. Right? So I don't want one person doing all the talking and the other two standing around going, "What he said." Right? So you each have to have a part. Got it? Now I know what you're thinking. This is statistics. Why do I have to learn to speak in public? Why do I have to learn to write papers and all that? We're trying to prepare you for life a little bit, right? When you get out on the job, you don't get to just sit in your corner at a computer and crunch numbers all day and never have to explain anything to anybody. One of the most important things I've learned from my time in industry and in academia is that communication skills are at least as important as skills in your particular subject area. I can be the world's best statistician, but if I can't explain it to my boss, I'm not going to get any promotions or raises, right? So, communication skills. You got to learn not only to do the work, but how to explain it to other people. So when you give your presentation, I want you to do it from the perspective of, these are not statisticians sitting in the audience. These are people who don't know and really don't want to know the gory details about how the mathematics works behind the scenes. So pick out what you think is interesting from a mathematical, statistical perspective, but I'm not looking for, a complicated talk with lots of mu's and betas and things like that in it, but just from a high level, explain the statistics and why certain variables are important, but when you control for another variable, it goes away. Discussion like that. I also highly recommend that in your paper, and I always say this to like students, like Taylor gave a presentation at a KME, once you get your final model, you should find in the data examples and then walk the audience through that. So, okay, here's my multiple regression model, saying if that's what you decide to do. Right? Well, remember so-and-so from 2012, and he did this, and he got paid this much. If we plug him into the model, here's what the predicted value for him is. And so then he picks somebody the model predicts really well, pick an outlier that the model didn't predict well at all, see if you can figure out real-life reasons why. It may have to do, well, then they got injured that year, or they were injured in 2011 when we were collecting data, but they were on a multi-year contract, so their salary's still real high, even though their numbers were horrible. Whatever. But get some examples out of the data that you can walk the audience through that help them understand how all this mathematical stuff works. Okay? Okay, so this was the first group, and it was, I got to remember, these were the non-pitchers. So guess what group 2 is?
Pitchers.
That's the pitchers. And, for pitchers, we don't care about their batting statistics near so much. We care about their pitching statistics. So for pitchers, it's earned run average and win percentage and, all that kind of stuff. Now, base on balls, that's them giving up base on balls instead of getting a base on balls while they're batting. Right? So we don't have batting statistics for them. We have pitching statistics. All right? But other than that, everything is the same. The 1992 data is a little bit more limited. There's not as many variables there. And I forget how I handled pitchers, non-pitchers. So let's see.
That's the one you didn't collect?
Yeah, this is the one that I got off the web. It looks like it's non-pitchers. So yeah, it doesn't really say, but it's talking about runs batted in and home runs, so it's giving batting statistics. Yeah, here it is. It includes following information for non-pitchers from the 1991 season. So Group 1 and Group 3 have non-pitchers. Group 2 has pitchers. Right? Now, it's kind of interesting, or it might be kind of interesting. 1992 for one data set, and then 2012 for the next. That's 20 years difference, right? So it'll be interesting to see, did things change in 20 years, or are the same things still important? I think you'll see that the average salary went up a lot in those 20 years, but maybe the things that predict salary are basically the same. It'll be interesting to see that. All right? So, how are we going to divide up into groups? Is everybody happy with the groups they had last time?
Yep.
Your group's not here. Let's see who's in your group. Nate and... Okay. So it was the 3 girls, these 3 guys, and then... Okay. Yeah, I don't care. That doesn't turn... Yeah. So that's fine. Now, to decide who gets which data set, I don't know that it makes a whole lot of difference. But...
Hold on. We've been talking about how you guys...
Ladies first.
How you guys are smarter at everything, so
Yeah.
you should get the hardest data set.
I think I
Oh no, now we random generate.
Yeah, I'm going to randomly generate.
But you said that women's IQs are so much higher than men's. You just
Statistically, they should get the harder homework. It's best for them.
Well, I don't know that any one of these is harder than the other. I really think they're pretty comparable. So what I'm doing here is I'm generating a random integer between 1 and 3. The first one that pops up gets project number 1.
Wait, what group is 1, 2, or 3?
Well, that's a good suggestion. We better number the groups. So you guys are group 1.
Take that.
You guys are group number 2, and the girls are number 3. Right? I just had to contradict what Emily said.
It's like the least effective way possible.
All right, so they're going to go in the order here. So group, the projects are numbered 1, 2, 3. So now I'm matching your group number to that, right? So group number, or project number 1 data goes to group number 2. Right? So you got to remember that. You're number 1. Number 1.
What does it take to be number 1?
Then the next group is group number 3. So you got the pitcher's data. Okay? So then by default,
I get the one
you guys get the, what?
I get the one I didn't want.
You get the old 1992 data, right?
I wanted your data.
Who's in my group, by the way? You and
Nick,
Did you just say
he's
that?
just off the conference. So
No,
Yeah.
he's go the ball.
Okay.
Oh my God.
do not know what a pitcher is.
No, I don't watch baseball. Oh. It's okay.
Are we sure you can check the groups now? Feeling so confident?
She doesn't know what a pitcher is. That's terrible. You guys are going to have a lot of fun, I can tell.
I have never seen Dr. Mosier be surprised by a question.
You know, I shouldn't waste time on this, but it's, you know, in my other life, I have to travel a fair amount for business and with pharmaceutical companies and such. And this is not a racist thing to say, but a lot of the people who get PhDs in statistics are Asian, right? Very, very smart people, right? And so I had the privilege of sitting in Fenway Park at a Boston Red Sox game with a guy from China who worked the same company I did, and we were good friends and everything, but he not only had never been to a baseball game, he had no idea what the game was even about. He just, you know, the group of us say, hey, we're going to go to Fenway. We're going to go to a ball game. So we were all excited, and he's like, okay, I'll go. So I sat next to this guy, and I literally had to explain, okay, the pitcher's going to throw the ball. See that little white thing on the ground? It's supposed to go over that. If it does, it's a strike. Okay, what if it doesn't? Well, then it's a ball. Okay, so 3 strikes, 4 balls, I mean, he knew nothing about it. He didn't even know which direction you run after you hit the ball. And so it was really kind of neat to have to, because I don't remember not knowing that stuff. I mean, from 3 years old, you're out there with a wiffle ball, you know, and you know which direction to run. So it was kind of cool to do it. So if you don't know anything about baseball, this should be interesting.
Explain it to her.
Yeah. So learning to explain things is a great art, as I said. There you go. All right. And you're buying tickets?
This break,
Oh, here. Okay. Gotcha. Okay, so let's move now to chapter 17. And let's see, I need this thing and I need my notes. So I'm not going to have today to using SAS to do these things. We'll only get through basically the terminology today, and then we'll probably be out of time. But I checked right before class, and SAS Enterprise Guide did incorporate the quality control type statistics. So you can do everything within that. It's got a few slight differences from what our textbook has in terms of the way things are computed. As always, that's always been the case. The statistical software like SAS tends to have the more updated, more refined versions of things, but they're more complicated, so textbooks tend to teach at an intro level the less complicated version. But so actually, let me pull up here. I want to use some of their pictures, and what I have, I've said before that. I said before that since you guys now have the ebook, you don't get to have PDF files. But this is the PDF file of the last edition of the book. So we are on 8th edition, I think. So this would be 7th edition. And I want to get past all this stuff and get to a graph. There. Okay, so a little bit of an intro into the topic. That you'll hear the term in control or in process. All right, so quality control deals with usually a manufacturing process, but it doesn't have to be. These methods can be applied to anything where you collect data over time and you have metrics that have to be met. Right? So it could be somebody who runs a tax preparation business. And okay, when somebody comes in and they plop down their shoebox full of receipts, how long does it take me to get their tax return done? And then are there errors? If so, how many errors were there? So you're tracking metrics of how well things are done, right? And so you predefine some idea of what's acceptable amount of variability or acceptable error rate or whatever it is, and then you track it over time. And often in manufacturing, it's the mean. This says something about water resistance data, so I think this is something about filters. So they have a certain amount of water resistance that filter's supposed to, a maximum that filter's supposed to have, or whatever. But they track it over time. So they take a sample, and they compute a sample mean, and they plot that sample mean, right? So they predefined limits for what's considered in control. So as long as we're producing, whatever it is we're doing that's within the limits, we're fine. And over time in a manufacturing process, it may tend to start to drift, right? So like the machine is getting out of calibration or whatever. So think of filling pop bottles that are coming down an assembly line. It's supposed to be 12 ounces go in each bottle. right? So, okay, it starts off at 12, but it may start to get out of calibration and start to give a little bit more and a little bit more. So you're taking samples off the assembly line. Maybe you grab, every 3 hours you grab 5 bottles. And you say, what's the mean of those 5 bottles? So you plot that, right? So what this whole chapter is about are statistical ways to decide, is our process of filling pop bottles still in control, or do we need to make some adjustments? And they can even program the machines to alert the people when, hey, it looks like things are out of control here. And it'll send off an alarm, and they'll shut it down, and they'll tweak the machine that stops when the bottle or when the pop is coming out of the machine or whatever, right? So that's called process control. You're controlling the process. So let's get some terminology out of the way. So this whole chapter is called, or is about, statistics for quality. I think I mentioned last time I was just starting to talk about quality control. And I mentioned a guy named D. Edwards Deming. Do you remember me talking about Deming?
Yeah, I said that.
I was probably talking with you after class, maybe that's what it was. But there was a professor at CSU that was a student of Deming's. And when I was a kid, I grew up in the 60s and 70s, right? So when I was a kid, if you got something like a toy or whatever and you turned it over, and it said made in Japan, the common stereotype in the United States at that time was, oh, then it's a piece of junk. Right? Made in Japan.
They make all the best stuff.
Yeah. And so now, what do you think of when you think of things that were made in Japan? It's all the best stuff. They got better cars, they got better cameras, they got better cell phones, right? Everything. Well, Deming, the guy Deming, was almost single-handedly responsible for that turnaround. After World War II, after we bombed Japan, the United States went in and tried, okay, let's get them back on their feet now, right? So, and so this guy Deming went over there, and he was hired by a lot of Japanese corporations because he was a statistician to help us figure out how do we make high-quality products. And during the 60s, but really into the 70s, they surpassed the United States in terms of quality, and their sales shot up. American sales of the similar products went down, and then America started to catch up in the 80s, like, ooh, I guess we better worry about quality, right? And so today, to this day in Japan, there is one of the highest awards you can get in industry is the Deming Award. Right? They call it the Deming Award, and so whichever company seems to have is rated highest in quality, they get the Deming Award. It's a big deal in Japan. Yeah.
On a side note, in that process, we found out that their way of operating businesses is actually superior to what we were using. So we came out with a lot out of that exchange.
So it's not just manufacturing, it's also just the way business is conducted. Yeah, interesting. Yeah, very good. So what did Deming do? He realized that every step in a process has components of that step, and if you can tightly control those components, put your efforts in things that can be changed or that can be detected numerically and controlled, then you end up with a better product at the end of the process. Right? So the word process, what does that mean? So a process is a chain of activities that turns out, and this is jargon, that turns inputs into, guess what? Outputs. So basically, think of a manufacturing process. You've got raw materials going in. You've got a finished product coming out. You've got inputs and you've got outputs. So all of the steps that go into changing your raw materials into your finished product, that's part of the process, right? So one of the things that they talk about in the book, or they show in the book, is called a flow chart. Now, you've heard that term probably 100 times, and you computer science people use flow charts when you are first thinking about, okay, I need a program that'll do this and this and this. You write a flow chart, right? Well, it's the same kind of idea. It's just basically a figure or a picture of the stages of the process. So it's at a fairly high level, right? So you can think of, if I'm manufacturing bicycles, there's an awful lot of steps to go from raw materials, right? So the flow chart is at a higher level. It's not going to talk about, well, then we weld this piece to this piece, and then we sand that weld down smooth. Things like that aren't in the flow chart, but it's at a higher level.
We got that discrete math, don't we?
Yeah, discrete math uses operations research kind of stuff, uses a lot of flow charts. Okay, I'll show an example here in a second from that PDF file of the book. Actually, why wait? I can do it right here. So let me scroll up. This is a flow chart, and I gotta get. There. I just got to learn how to use it.
Also, Dr.
Okay.
Taught that.
So let me scroll till I find. Whoa! I did something. Yeah, here we go. So this is a flow chart and cause and effect diagram. So we'll talk about that in a second. Of a hot forging process. Ooh, what is that? Hot forging process. Yeah. So. The picture here is kind of a clue of what they're talking about. They basically melt the metal alloy, and then they pour it into molds, and that's forging, right? They're creating something out of metal. So it involves heating metal to a plastic state, meaning flexible, and then shaping it by applying thousands of pounds of pressure to force the metal into a die, which is, that word die in manufacturing is basically a mold. It says a kind of mold, right? So figure 17.2 is a flow chart of a typical hot forging process. So here we go. Step number 1, receive the material. Okay, you got to get the material. Then what does a diamond shape in a flow chart mean? What did you say? Yeah, like a selection or a decision. Right? Yeah. So a condition. So it's a yes/no answer to it. So it's usually a question. Check for size and metallurgy. Okay? So I would have put a question mark after the okay. Is it okay? If no, scrap it. Hopefully in a quality control situation, scrapping it means you haven't paid for it yet. Right? So this is like acceptance criteria. You inspect it when it comes off the truck. You scrap any that don't seem to meet. So that's an opportunity for quality, right? So get rid of the bad stuff. Then cut to the billet length. Okay, I don't know what a billet is. Well, a billet is a chunk of the raw material of the metal, right? So it comes like in long rods kind of things. They call those billets. And then deburr the billets, so get the rough edges off of it. Then check if the size is okay. If no, if it's oversized, yes, oversized, cut it to length again, right? So you've got a loop in there that checks your quality. Right? If it's not oversized, but its size is not okay, that means it's too small. It means you overcut it, scrap. Right? So loss of money, loss of money. Then now we go to the heating part. Heat it to the required temperature, forge it, flash trim, all these things. We don't really care what those are. But then check it again. Yes, if it's okay now, you're done. So put a barcode on it and send it to the store. If it's not, scrap it. Well, what happens if you scrap at this stage? A lot of time and money wasted. Perfect way to say it. Right? You scrap it early, you haven't at least invested any time. But here, you've gone through all the steps, and you still have a product that's not quality enough to sell. Right? Now, where the Japanese got ahead of us, and the United States kind of got a bad reputation for a lot of manufacturing, was they weren't scrapping here. They weren't really checking the quality of their final product, or if they were going ahead and selling them. Right? So they put a car out there on the lot, sell it, but then it craps out in a few months. Well,
VW just get burned with this?
Well, no, VW wasn't a quality problem.
They weren't testing.
What was the VW? Does anybody know what the VW problem was? Go ahead.
They programmed their cars to sense emissions tests, and then it would kick in higher emission standards. But you get better gas mileage when you don't worry about emissions. So all of the other times when they weren't testing emissions, you'd be getting actual mileage. Yeah.
And I had a Volkswagen diesel Jetta, which is the car that was the problem. Mine was actually a few years older than the years that they talked about, but no doubt it was still going on back then. So that wasn't a quality thing as much, but it's sort of shortcutting here. Check the emission standards. If they're checking, then you can put one out that doesn't meet it, but you can trick the computer to say it does, and you can go ahead and get it out there. But what happens if you don't have this step and you don't scrap here, then your reputation goes down, because people talk. It's like, man, I bought a Chevy and that thing was a piece of junk, right? Well, then gradually their sales are going to go down, right? So this is an important step, even though this is very costly, but it's still an important step. But Deming's whole philosophy was catch it early. Don't come down here where this check, almost all of them say, yeah, this is quality, sell it. So there's hardly anything happens down here. Okay, now the other graph that they talked about was a cause and effect diagram. So let me see if I have room down here. Cause and effect diagram. And this just organizes the logical relationships between the inputs and the stages. It's a way to get it down on paper. Basically, it's organizing your thoughts. And these are sometimes called fishbone diagrams. And I'll show one here and you'll see what I'm talking about. Organize the logical relationships of the inputs and the stages. Inputs and stages. To the outputs. That doesn't look like very good writing, but so let's go back to here and look at one of these diagrams. This will be easier if I use my mouse, so I can scroll quicker with it. There. So do you see why it's sometimes called a fishbone diagram? So you have this main line going, that's like the backbone of the fish, and then you have the ribs coming off of that. So at the end here is your output, a good forged item, a quality forged item. So these are all the things that can cause a problem. So cause and effect diagram. So you have big categories. So the environment. How can the environment of the room that we're doing the forging in affect things? So humidity, if there's dust in the die, the quality of the air, all those things could maybe cause a problem with the heating of the metal. The material, the metallurgy of it, does it have the right components at the right percentages? Is it this much iron and this much molybdenum, or whatever? The size of the billet, that's all part of the material. The temperature, the personnel, I mean, they decide the temperature settings. They handle the material. They take it from one stage of it to the next, and so on. So all the things. So this is a lot of times put together by the quality assurance team or department before they ever start the process. They sit down and basically they're up at a whiteboard drawing pictures, saying, okay, what else can you think of that might have an issue? Right? Now, we won't talk about it in this chapter, but there's a whole area of statistics that deals with industrial type experiments, but you can design experiments to figure what are the best settings to use for all these things. Well, if we dial this one into here and get the temperature to this and the pressure dial to here, what combination of those things produces the best output? And it's really part of the quality process, but not what we're talking about here. Okay? So any questions on a cause and effect diagram? All right, so I see I have run out of time. So that's just kind of introducing the process. Next time we'll talk about how you actually then use the statistics from samples to make sure that the flow chart and the cause and effect diagram are tracking appropriately. All right, so no class on Friday. Work on your projects, and we'll see you next Monday.